Hello, everyone. Thank you for joining our webinar. Today, we're going to talk about how to develop mobile applications for drones flying PX4 with the new SDK. My name is Carlotta. I am the marketing manager at Auterion. And for anyone not familiar with Auterion, we are a company that builds the open source operating system for commercial drones on top of PX4. So let's move on to our panelists. Our presenters today are Dr. Lorenz Meier, Auterion's co-founder and creator of PX4, Pixhawk, QGC, and MAVLink. Jonas Vautherin. Jonas is a software engineer at Auterion, and Julian is PX4 software engineer. Both of them worked on the development of the SDK. Moving on to today's agenda, we will share with you a brief introduction from Lorenz on the history of PX4 and a short introduction to Auterion. We will then continue with Jonas and Julian that will introduce the concept of the SDK, what the goals were and how they architectured the software. And finally, they will show you how to write apps and control PX4 powered drones from a convenient SDK with a couple of examples in the different coding languages. I will give now the word to Lorenz.
Hi, everybody. Thanks for joining. It's really exciting to see 61 people already online. I'm sure there will be joining more people in the next few minutes. The reason to do the quick history and introduction is that the SDK is the first time that we're exposing more of this ecosystem to a broader audience to integrate PX4 powered drones in more use cases. And it's probably useful because you will likely have seen industry terms around to have a rough idea what means, which terms refer to these ecosystems and what the components are. So Pixhawk is the hardware autopilot that's used by many different companies and also by the development community. That is something I've created in 2008. MAVLink is the communication protocol. You can think of it as the HTML of drones. It's a binary, highly efficient protocol created in 2009, also something we've architectured. Ground Control is the ground station application that we're using. This is the one that you will replace with the SDK, but it is what is the baseline implementation for the control of drones. And last but not least, PX4 is the flight control software running on the hardware. And it doesn't just run on Pixhawk, it also runs on other platforms. And so PX4 is the main target for the SDK because that defines which functions are implemented on the autopilot. We've seen in the last years a tremendous adoption of PX4 in consumer drones, like in this model from Yuneec, in commercial drones, like this model again from Yuneec, in vertical takeoff systems like the Wingtra 1, and even in advanced applications, which also could be powered by the SDK, like, for example, this cargo drone from JD.com or this cargo drone from DHL, which are new use cases. Then you've already seen there are a number of software components in this. They are all interfacing to PX4, which is essentially the kernel of this. Like the Linux kernel is the central part of a Linux system. But as on Linux, you don't have just the kernel. You also need a lot of other software packages to really do anything. And in the same way, we have a whole stack of software around PX4, which you need to run on the autopilot or to interface it with the SDK. You can use the SDK on a mobile phone or on board. We've put this here in the block diagram accordingly. That matches mostly the use case. The technology is always the same, no matter where you run it. And then what I also wanted to introduce is Drone Code. That's essentially the industry association of PX4 adopters. And that helps us to mingle with companies, understand what the need is, and connect adopting companies with the development community. Last but not least, a quick introduction of Auterion. I don't want to make this too commercial, but as we've invited to the webinar, we also wanted to make that really transparent. Auterion builds a managed distribution of PX4, like Red Hat builds a managed distribution of Linux. That includes also management tools in the cloud to manage a whole drone fleet. And we contribute a lot to the open source development, including new features like obstacle avoidance using computer vision, or we perform things like deep learning based predictive maintenance for our customers. And that is essentially the reason why we're hosting this webinar today. Vautherin is the largest contributor to PX4, and the company invests into education and training, and this webinar is part of that. As you can see, there are also many other contributing companies and a very broad community of individual contributors and consultants, which, as the creator and maintainer of PX4 together with Daniel, is really fantastic for me to see that we have this really broad base, but also really strong players behind the ecosystem. And with that, I'm handing back, and thank you all for joining. We're at 81 now.
Okay, thank you very much, Lorenz. We will now send over the first poll. So I'm launching the poll. Everybody, please answer to the first question. If you're currently using PX4, this question will help us to understand the level of expertise on PX4. Awesome, I see you answering. Okay, I see that the majority of you are PX4 users and many of you are also contributors. This is great. And to the people who would like to learn more, if you have questions, please address them in the Q&A sections and we will try to answer as many as possible. I will now hand it over to Julian.
Okay, hi everyone. So as Lorenz mentioned before, Q ground control is an out-of-the-box application with a broad set of features. And however, what if you need a specific application or you have a specific need or user interface for your use case? How can you achieve that? Well, you need communication with the drone. So how does that work? The answer to the question is, as expected and already mentioned, MAVLink. MAVLink is a communication protocol. It's an industry standard and used by PX4, Q ground control, etc. Now, MAVLink has a broad set of messages, and it is very powerful in functionality. It is used to receive telemetry, send commands, set parameters, upload missions, etc., etc. However, this means that it's not always clear which messages and settings are actually supported by the autopilot. And we can't always be sure which parameters are actually tested and in what range. Additionally, MAVLink has sort of internal protocols. For instance, the mission protocol. So here we see the sequence diagram of a mission upload. It starts with the ground station sending the waypoint count. Then the autopilot requests the mission items one by one. And both parties need to check for timeouts after every transmission and retransmit messages if they get lost. This is quite cumbersome to implement and error prone. So clearly this is something that a developer who just wants to automate a flight or just write an Android or iOS application does not want to mess with. And all such a developer really wants is a simple, stable API. So really it should be as easy as this. We see C++ on the left here, Python on the right, and both times we upload a mission. And all we do is we create a bunch of mission items and upload them. And we don't have to take care about the exact protocol, about retransmissions, about what's actually supported. All of that should be taken care of under the hood. And with this in mind, we started working on the Drone Code SDK about 2 years back. And there are quite a few other requirements on top of just this simple and stable API. So the SDK also needs to be usable in different programming languages, C++, Python, Swift on iOS, Java on Android, just to name a few. And on top of that, it needs to be cross-platform, so work on Linux, macOS, Windows, Android, iOS. And it should also be extensible, so support new use cases, allow additions in the future. So with this in mind, it's not quite trivial to satisfy all these requirements, and therefore we want to dive into the architecture for a little bit and explain how we try to satisfy all these requirements. So let's say we're communicating with the drone either via Wi-Fi or a 3DR radio using MAVLink, and so there's MAVLink communication. And this is all taken care of by a core of the SDK. Then around the core, we have plugins, and those plugins are responsible for certain aspects, certain features. So here we just list a couple of the plugins, the most important ones, starting with telemetry to get information about the drone, get feedback. Then we have action to send commands to the drone, such as arming, takeoff, land, return to launch, or for VTOL, we even have commands to set transitions, so from multi-copter to fixed wing or back to multi-copter. A mission plugin to upload missions, as we have seen it before, and also to receive the progress while a mission is flown. The camera plugin to take pictures, but also to set all of the different camera settings. And finally, the offboard plugin, which allows for offboard control. So what we mean by this is that you can control, for instance, velocity or position set points from, for instance, an onboard computer. So this core and the plugins is basically a C++ library. It's written in C++ 11. And so now we get to the different programming languages. And basically around that, we have language wrappers, as we call them. In this example, it's Python, Swift, and Java. Now these language wrappers are implemented using gRPC messaging. On the C++ side, we have a gRPC server. And in the respective wrapper languages, we then have a gRPC client. And right now, the wrapper code is actually auto-generated. However, the server code is not yet auto-generated. But that's something that is planned for the future. And we call these two pieces the backend, so the server side, and the front end, the client side. Now let's also quickly look at how this configuration could look like. The first case is the simple case. We have just an autopilot, so just the Pixhawk on the drone, and it communicates MAVLink to the ground station. And in this case, we have the SDK backend and the SDK frontend both running on the ground station. A ground station could be a tablet, an actual computer, a phone, you name it, on the ground. Now, for the case where you have a companion computer, so another computer running on the drone, then you can have the SDK backend running on the companion computer and actually communicate or transmit, rather, gRPC between the drone and the ground station. So you have the backend running on the companion computer, front end on your phone or the ground station. However, we are not trying to to set that in stone. Everything is flexible. So you might as well continue to talk MAVLink and have the backend and front end on the ground station. So really, this is flexible and can be applied however needs to be. So you might think this all sounds great in theory. We are actually proud that we have done an integration with this architecture. We have the 3DR side scan, which is powered by the SDK, and that's running on iOS, communicating via MAVLink with the Yuneec 8520, which runs PX4. And this is collaboration between 3DR, Yuneec, and Auterion. Okay.
Okay, thank you very much, Julian. And I'm gonna run now the second poll. So everybody, please be ready to vote. Okay, launching now. Ten seconds more. And this question will help us define the future roadmap of the SDK, so please vote. Okay, I just ended the poll. I see that the majority of you answered with write my own app for drones flying with PX4. And this is something we will definitely take into consideration. And please, I'd just like to remind you that you can send your questions in the Q&A box. So I'm gonna hand it over to Jonas.
Okay, great. So let's now look into some code. And for that, I guess we can directly try to go in a live demo. So I will start with some Python. And I just want to say first, we have essentially two ways of communicating with the drone, or like exposing an API. One is we have synchronous calls, where you just call, so you send an action and then you wait for receiving the answer. And we have, you can have an asynchronous API where you just send a message and you continue doing your stuff until you receive the response to that. In Python, we happen to have both of those. And I will show the synchronous one where we do polling. You'll see later that we have asynchronous in other languages. Before I start the demo, I'd like to explain a bit what simulation setup I have. So it works like this. We have two boxes in this graph. On the left side, we have the PX4, which is the actual autopilot code that is running on your drone. And on the right side, we have the simulator. So it could be Gazebo, JMavSim, or others. And the role of the simulator is just to simulate the sensors and send that information to the autopilot. So that the autopilot thinks it's actually flying. And all of that is running on your host computer. So you can just, yeah, it's really convenient for development. So let me now share my screen and start writing some code. Good. So what's happening here? Okay. So let me first start a simulator, right? So I'm just running the firmware code, running JMavSim from here. Let's just wait for it to start. Good, and I will just hide that. Okay, right. So here on the left side, I've got JMavSim. We have a drone, simulated drone on the ground, and I've got like my terminals on the right. One thing I need to do, we talked about front end and back end. So I need to start the back end, and then I will connect Python to that. So here we have our back end that is discovering the drone, and I can now go into Python. So, okay, let me start the shell and start writing code. Julian has been exposing a few plugins first. We will try to use now only action and telemetry. The reason for that is just that they are both quite different. Action is like sending just commands to the drone, and telemetry is receiving messages. And that's actually representative of most of the plugins, or like all of them. It's the two kinds of messages we have. So here, let's start. So I will just import the action plugin. I import action, and I instantiate it. So in Python, it's quite easy. I just create an action object, right? And then from that, I can directly use this synchronous interface. So I will just say, okay, action.arm, and it arms the drone. And I continue after that. I just take off. We see that the simulator is just taking off. And that's good. And that's the way you send actions in Python. So now let me just try to receive information from it, and we'll go for that on the telemetry. So I do the same thing. I import the telemetry and I instantiate my plugin like this. And from here, I can start pulling stuff from the drone. So here I'm interested in the position. So telemetry.position, and position has multiple fields like latitude, longitude, stuff like that. So I'm interested here in relative altitude. So that would be relative altitude in meters. So I just get that, and I get the altitude of the drone. It's now at 2.5 meters. Well, so that's for polling. The thing is that if now I want to monitor this altitude, I can just go on and write a loop for that. So let me do exactly the same, but in a while loop. Okay, and I run that. I'm just receiving the altitude of the drone. And now if I go back on the upper right corner and just ask the drone to land, if you observe the numbers on the bottom right, so it's at 2.5 meters and it will land. So it should like decrease to 0. And that's what we are seeing now, 2, 1, and then 0 landing. Okay, so that's for the Python demo. So let's go back to the slides. Yeah. So I have here, that's basically the code I've been running, just in case the demo is not working, but let's skip that now. Yeah. We've seen Python, quite easy. Now let's have a look at iOS. And iOS is a bit different in the sense that it's an asynchronous API. So it's really, it looks like you give a callback to the API and you receive events in return. But instead of doing that, what we do here is we use streams. So we use reactive extensions. The library is called RxSwift, and it's really an implementation of streams. And a stream is just a sequence of events you receive. So the stream of positions is just events like you just continuously receive the position of the drone. So let's have a look at some code. Like we say we have, so in Python, we had only action and telemetry I mean, we directly went into action. Here we need to instantiate the score plugin. So we just create it, let core equal score, and then we have to start it. And in RxSwift, we first create our stream object, and then we have to subscribe it. So core.connect, and then we add subscribe. You'll see subscribe a bit everywhere. It just means that we run the command. Okay, so if we then look at the action plugin, we just create the action plugin, let action equals action, and here we have to give an address and a port. I'm running the backend in this example on my computer, so it's localhost and the default port. And then I can just start doing stuff. So arming is just action.arm, and because it's RxSwift, we subscribe, action arm subscribe. And the good thing with those streams is that you can compose functions on top of that. So when I arm, I may want to know if it worked or not and print something. And that's what I do here. So before I subscribe, I just say, okay, from my arming completable, it's called a completable in Swift, in RX Swift. I just say, okay, do, on error, you do something. That's some kind of lambda expression. So I print arm failed. And if it works uncompleted, then I say, okay, arm succeeded. Quite easy, right? And we can continue composing events like that. So usually I don't just want to arm. If I arm, it means that I want to take off. So in this case, I just want to say arm, and when it completes, so if it doesn't fail, I want you to take off. So I say arm dot and then, and here I say take off. And then in this example, I want to do a bit more than that. I want to land after that. So I just wait for 8 seconds. So that's this delay operator, delay 8, and then action land. Okay, so that's for doing the same thing as we were doing before in Python. We just arm, take off, and land. And just as we were doing before in Python, let's look at the telemetry. So same thing, we initialize telemetry objects. Telemetry equals telemetry. We give address, port, and then we start getting the position. And this time we are not polling it, so we will not need a while loop, but we get a stream. So telemetry.position observable is this observable. So that's a stream in RX Swift. And I just say, okay, for every time you receive the position, I want to do something. So I say do on next. And here my lambda says, okay, for each position I receive, print the position. And I subscribe. And what I will get from that in the simulation where I take off and land is that kind of thing. So I will see that I receive position objects, and those objects have a latitude, a longitude, relative altitude, and an absolute altitude. And yeah, just as before, let's say we are interested in the relative altitude, like the third field, and see what we can do to just get that. So I use another operator, which is map. So, and map just transforms each element that is arriving in another element. So here I say, okay, my position observable, I want to map the position and say for each position I receive, I just want to return a round position relative altitude m. So I just take the relative altitude and I round it, and then I get a new stream from that, which is a stream of rounded relative altitude. Same thing, I just print it this time as the altitude. And if I do that while taking off, I see that I receive multiple times 0 meters, 1, 2, and then 2. And that's very convenient already, but I'm not necessarily interested in receiving those events multiple times. I receive 2, like 8, I don't know, 10 times. So what I can do is that I can continue composing stuff and just say, okay, just after my map, now that I have my stream of altitudes, I want to say, okay, just give me the distinct elements. So as long as it doesn't change, just don't tell me anything. But if it changes, send me an event, and I show it. And in this case, I will just receive what we could expect. So just 0 meters, 1, 2, 3, 2, 1, 0. That's takeoff and landing. Great. So let's try a demo of that. Let me share my screen again. Good. So same as before. So I need to run. I'm still running on JMavSim. So I will just run JMavSim on my computer, and it will take a few seconds. So the setup I have here is that I have JMavSim running on my computer. I have a simulated iPhone on the right side, and I will just run on like our example app for the SDK. So we have here the drone on the left side, and let me just compile and run the app. So we are now in the project of the app. I'm just starting it, and just to show you, like we have some of the code of the map here, and it really looks very similar to what we've seen. It's basically always that you just get like an RX Swift object, completable, observable, or something. Then you compose stuff. Here you have do, or like others, map, other operators, and then you just subscribe to start it. And that's all you need to start like working with that. But it's obviously much more powerful than that. So you have many operators that you could run. Okay, so here we have the simulation running. We have our example app here that is getting the telemetry. So we see that the drone landed. And we have an action tab that is just demoing all of that. And here I can just say what I did in Python. So we just arm, okay, succeeded, then it should take off. And I can land. So this time it's really like, it's just an iOS app. And just a bit more than we did in Python, I just want to show the mission example. So here we have a mission that's defined with a few waypoints. You see here, it will go from start to stop. So what I can do is that I just upload the mission. So it uploaded like those 4 waypoints, and I would just start it. So now we see that the drone is taking off, and it will just go to those waypoints. And during the flight, I can just get the count. And here I see that I have 4 waypoints. I can ask, is the mission finished? Those are all like features that are exposed in the API. So yeah, let's just wait a few seconds to see the drone moving. And that's it. And this example app is open source, and if you're interested, you should definitely go check the repo. Okay, let's go back to the presentation. Good.
Awesome, thank you very much, Jonas. We're gonna now launch poll number 3. So what language are you likely to use SDK? Couple of seconds more. Awesome, ending the poll now. And I see that the majority are likely to use the SDK for C++ and Python. So handing it over to Julian again.
Okay, so let's look into C++ as well. Here we also wanted to give you a quick impression how the interface looks like. And for this, we have a very simplified VTOL example. So the goal is actually to just take off in multicopter mode and then transition to fixed wing mode. And what's going to happen at this point is the drone is a plane. Will just sort of circle, loiter around the takeoff location. And at that point, we can send it a go-to. We can send it a location and have it fly south. So in our case, we want to try to make it fly to the Lake of Zurich, actually. So let's look at this step by step. As usual in C++, we include the headers of the library, and then we want to be using the namespace of the drone code SDK. So then we just instantiate the SDK, and we add a UDP connection. So this is the UDP MAVLink connection to software in the loop to the simulation on port 14,540, which is an extra port running for things like the SDK or MAVROS next to the default port connecting to Q-ground control. We get a system, we get a reference to the system actually. And in this case, we just instantiate one plugin, we just need action for now. And this is very simplified, the steps that we want to take. As seen before, action arm, action takeoff. In this case, we just sleep a bit until the takeoff is done. Alternatively, this could be much better. So we could check for, is the takeoff complete? Or we could check for, have we reached a certain altitude? for simplicity here, it's just asleep. At that point, we transition to fixed wing. So as I said, it will transition to fixed wing mode and start loitering around the takeoff location. We then send it a go-to location. So it's this latitude, longitude of the mentioned point in above the Lake of Zurich. And then not a number twice, which here just stands for the altitude. We're just going to leave it at the current altitude, meant by none, not a number. And then also a heading, which we don't need here. We wait again. And in this example, actually, we don't want to fly all the way. It would take too long. We don't have to have you board. So we'll just transition back to multicopter and let it land. So you've probably seen that I omitted all of the return results of the function calls. So this is what it actually would look like. So in this case, we arm and we get an arm result, and we are then better off if we actually check the arm result. And if it's successful, we're good. We can continue. If not, then we might try again or do something else with the result that we get. So this is an machine readable enum, and then as well a human readable string for the error that happens. So that the string can be accessed here with action result str. Okay, let's switch screens and try this in real. Or not real, in simulation. Okay, so I have Q ground control open here just for comparison, so we know what's going on. And I'm going to launch software in the loop simulation, Gazebo this time. This is starting up. This is the Gazebo standard VTOL, so this is the Delta Quad being simulated. And over here on the top right, I have the example ready. So this is not exactly the code we were looking at before. There's an additional few printfs and some error message checks, but it's more or less what we've been looking at before. So let's run this and see what's going to happen. So we see that we are here at the usual software in the loop, start location. Okay, arming taking off. Here we go. I'll try to zoom out to see where it is. There it is. And we just transitioned and it flew out of sight on the Gazebo side, but we can monitor where it's going on the QTC side. And as expected, it is now loitering around the takeoff location. And we are just waiting here for a bit to see how it's loitering, and we'll at some point then send it the location that we want to go to. So we're going to fly south. Still loitering now. You can see it on the bottom left. It's just passing around. A couple of pixels moving by, and we're off again. And now we sent it towards south. It's going. There are a couple of messages that it lost GPS for a while there. This is probably because Zoom is watching and putting some strain on my computer. Still seems to be going okay though. And at this point, we transitioned back to multicopter and we're stopping. And now we are going to descend and land where we are in multicopter mode. See if we can actually switch to the vehicle. Follow it. There it is. Soon we should see the props stop spinning, and so it has landed and disarmed. There we go. Okay, at this point we can switch back. Okay, so this is what you were supposed to be seeing. We can skip through this. Taking off, doing a loiter, flying south. Okay, okay. So, resources. How can you get the code? How can you get documentation? How can you do this yourself? We have listed here some links. The repositories for Python, the repository for Swift, and then also some notes on the reactive extensions, RX Swift, that Jonas mentioned. Make sure to have a look at these. C++, that's sort of the core SDK repository. Make sure to check that out. And it's noted here that most documentation is to be found in docs. So sdk.dronecode.org. Hamish is doing a great job there, helping with the docs. And so most of the instructions are over there and not in the READMEs. Just keep that in mind. And if you do have questions, do not hesitate and join us on Slack, and make sure to join the SDK channel. Jonas and I are almost always there to take questions and try to help. If you don't necessarily want to ask on Slack, you can also ask on the forum, on the discourse forum. Okay. At this point, we would also like to call for contributions. So please, when you start using this report box, this is probably the easiest one. You can help with documentation if you find anything unclear. You can make a pull request, you can ping us. Don't be afraid. You can help with examples. There's only a few simple ones for now. We can have more in the different languages. There are a bunch of tests. Some are passing, some are not. This is always work in progress, and we can appreciate your help. And same for continuous integration. We have Jenkins set up, Travis, AppWeir for Windows, some Docker images to build what you need, but lots to do there as well. And of course, if you need specific features for the SDK, ask us if it's something that makes sense. Make a pull request. Anything is welcome. We are open for suggestions. Yeah, we can always add plugins. So please don't hesitate. And at this point, we also would like to thank all the contributors, because it wasn't just Jonas and I, but many people that contributed over the past 2 years to this project, to the documentation, etc. It wouldn't have been possible without all of them. So thanks. And with this, I am concluding this presentation. Thanks for your attention. I'm going to pass on to Carlota.
Yes, thanks a lot, Julian. We will start now the Q&A session. We received a lot of questions, but please continue sending over the questions. We will try to answer as many as possible. So we're taking over the first question, and the question is, does the SDK support custom cameras, and is there a list of supported cameras? And I think, Julian, you can take over this one.
Okay, so the short answer is yes, it does support custom cameras. Is there a list of supported cameras? Probably not. So let me answer in detail about how this is possible. So the camera interface is based on the MAVLink camera definition. This is probably a bit too much for the scope of this webinar here, but it is very nicely documented on mavlink.io. There is docs, just look for camera definition, or hit us up on Slack, and we can help you. So what this means is you can have a custom camera with custom settings, and it will work with the SDK. This is based on parameters, and that a camera can advertise to the SDK, and the SDK then knows what to do. So this is quite powerful. And for the camera side, so not the SDK side, but on the camera side, there is the camera manager, which is sort of a reference implementation for a camera working with the SDK. You can find it in the drone codes or on GitHub. So GitHub. Yeah, on GitHub. It's called Camera Manager. Okay, I hope I answered that question.
Awesome, thanks, Julian. Moving on to the second question, we have a question around Java, Android, and the question is, when is it supported? And Jonas will take over.
Yeah, okay. So yeah, it's planned to support Java. I would hope to have it for Christmas. Realistically, I guess beginning of end year. And yeah, the idea is that we started with for the wrappers with Swift, and then we added Python. The way we did it is that in Swift we wrote like most of that manually, and then we started writing a way to auto-generate all of this. As Julian mentioned, the goal is to be able to auto-generate all of the front ends, and Python is a result of that. We almost auto-generate. I mean, we auto-generate all of that. The thing is that we still have, I mean, it's still work in progress. So we have to finish that and make sure that it works well for Swift and Python, and then we can move to Java. But once we have that, it should be really easy to add Java quickly. So yeah, to answer that, I would say beginning of next year.
Okay, thank you, Jonas. Next question is, do you plan to build onboard SDK and benefit of remaining backend on Companion? Julian, this is for you.
Right, so there's nothing stopping you in using the current SDK on board. Really, this is flexible. So whatever your use case, whatever your architecture, the SDK can run on board or off board. That doesn't matter as such. Also, you can always consider the camera manager as a thing that runs on board, especially if it's a camera, then that makes a lot of sense too. So really, you can put these pieces together for your needs.
Awesome. So moving now to the next question, why gRPC and what is it? Jonas, you want to answer that?
Yes. So gRPC is so that's this link we have between the what we call the front ends and the back ends. So just before I was opening this backend on my computer, before I connected Python to that, and the communication between those two is gRPC. So gRPC is a messaging project, and we chose that for different reasons, but we decided to completely hide it in the implementation. So the API we expose to users does not expose that at all, which means that it could be something else. Really, like it could be, we could decide at some point that 0MQ is much better and that we want to move to that, or somebody could try to do it. And that would not even like break the API or like existing applications. gRPC has multiple benefits. One of them is that it's built on top of protobuf, and it has this proto-C proto-compiler, proto-C. And they, like Google already generates that, generates the code in many languages, like really many languages. And we build on top of that. So what we auto-generate is we write a plugin for proto-C and generate all of the code from that. So that's one of the big arguments, just being able to support multiple languages. And then maybe another question that goes with that is, why do we do messaging? And the reason is that it helps. It adds flexibility, I would say. We can have multiple scenarios. So one is you run everything on your phone, your iPhone, say. If you run the front end on your phone and then you run the back end on the drone, then it can help you, like integrate the sensor without using MAVLink, for instance. You just do gRPC, and since we auto-generate that code, then it should be really easy to add new sensors and stuff like that. So yeah, I'd say that's for those reasons that we use gRPC for now.
Okay, great. So next question is for Lorenz. And the question is, what is the future roadmap of the SDK?
So this has very much been community driven, as everything we're doing. Community can mean different things, can mean by contributors, can also mean by interest of our users who we care about very much. And that is why we focused on Swift and Python. The overall roadmap is, however, to provide not just in language bindings, but also in features, something that makes drones easy to use and easy to integrate. And so definitely planning to support more, well, we do support full functionality on board already, but to make that more explicit, to provide more examples, so that you can use it also outside of a typical, for example, mapping drone application. And we will also see that one of the questions is also around how this differentiates from some of the other interfacing options to PX4, like, for example, ROS2. And so I think you can influence the roadmap of the SDK. Contact to Julian and Jonas. For now, we will definitely focus on Java bindings, other language bindings, and completing the examples for onboard and making it overall really accessible.
Awesome, thank you, Lorenz.
I would just like to add to this, if you do have specific requests or you want to talk through it, we also have a SDK working group call every 2 weeks where we can discuss things that should be on the roadmap or plan ahead, or you can just hear about what's going on as well. Okay.
Thanks, Julian. And now the next question is, which supported Python versions we have?
Yeah, that's a good question. So right now we support from Python 3.6 on, and there's a reason for that. It's just that we, as I said before, we have these synchronous and asynchronous APIs, and we built the asynchronous API based on async.io, which is part of the language, part of Python from 3.6 on. So we did that, and then we decided to build the simple, like, synchronous API on top of this, and that's simply the reason for that. We do it just because it's more convenient to maintain, but as we've seen before, there's like a lot of people interested in Python, and if we see that there's a need to support older versions of Python, we could definitely like auto-generate the code for Python, say 2, or like all versions of Python for this synchronous API. The asynchronous API, as I said, is based on async.io, so it will always be 3.6 and further. Yeah.
Okay, great. Thank you, Jonas. Next question. So is the DDS RTPS interface an alternative to gRPC or ROS2? Lorenz, you can take this one.
Yes, so somebody was very closely watching what we're doing in our community, which is really awesome. So we just, for the context of the full audience, we just released this week for PX4 native bindings for RTPS, which is the transport layer for ROS2. So you can publish from PX4 a topic straight into ROS2 and vice versa. That is something that Auterion has contributed, because it is the next generation interface for onboard robotics. The purpose of the SDK, or the use case of the SDK, is someone to allow to interface with a drone through a trusted, very stable interface. And for that, it's really awesome and the best thing you could possibly use. But if you want to connect components on board of a system, namely the companion computer and the flight controller, sometimes you need something that is much more closely interacting and much more closely interfaced than with just MAVLink. And for that, we have created this native ROS2 interface, which by the way also supports ROS1 through a bridge. And that is what I would recommend for things like obstacle avoidance or VIO for future designs, where MAVLink is limiting. MAVLink is really, really good for command and control links when you control a drone from a ground station or when you want to connect it to the cloud. And for that, MAVLink and the SDK will and are the best option.
Okay, Lorenz, and so we're gonna move now to the next question, which is, are other drone types also supported? And I think you can take also this one.
So we of course support any drone that runs PX4 and speaks MAVLink, with the caveat that there might be device-specific functionality that is not exposed on the SDK, but that's something you can easily contribute.
Awesome, thank you, Lorenz. And now the next question is, what is the maximum drone count? Julian, this is for you.
Right, so I'm assuming this is in respect to the SDK. There is two answers for this. One is for C++ and one is for the language wrappers. The C++ core of the SDK can support multiple drones at the same time with one binary. And this is based on the system ID that is transmitted via MAVLink. So it goes from 1 to 255, and that's basically the limit there. Now, this addressing multiple drones with one binary is not currently exposed in the language wrappers. So the language wrappers just go to one drone at one time. So there the limit is 1. But this also makes sense because once you start talking to multiple drones, it might not be super efficient to go through anything else than C++ anyway.
I would like to just add something to that. I completely agree with that. Just for the language bindings. So because we want the interface to be simple, for now we are not supporting like more than one drone. But that does not mean that from one app you cannot do it. Like you could instantiate just the plugins multiple times and connect to multiple drones. One thing that's important to me, I think, is there's a difference for me between controlling multiple drones and controlling a swarm. So if you're interested in like the drone count, I guess maybe that would be for a swarm. And in this case, to me, it's a completely different situation. Like you don't want to receive and process the messages from like 1,000 drones on your phone. So we would not solve that the same way. But if you say, I have a mapping app and I want to control 3, 4, 5 drones at the same time, we can do it. It's just that the way we do it in the language bindings or in C++ is a bit different, but we can do it.
Okay, thank you guys. Last 2 questions. So the next one is there a favorite simulator? Julian, you can take this.
Good question. It depends on what you're trying to do. If you need, for instance, to simulate VTOL, then Gazebo is what you need. If you have any vision requirements, if you want to test your vision algorithms, Gazebo is going to be the answer. If it's just a quick check, does it take off, does it do the mission? I personally usually tend to use JMavSim just because it's simple. So I guess I don't have a favorite. It depends on the use case and also on on your machine and if it's strong enough.
Awesome. And now I think you can take also the last one on how can people contribute.
Sure, please do. So as said, contact us on Slack or look at issues on GitHub. I'm sure you'll find things that catch your eyes that you want to improve or discuss. So feel free. Also, we are trying to add tags on GitHub to kind of show which issues might be good to be picked up by someone new in the SDK development. Right now we have tags, they're called help wanted. We might also add tags such as beginner or easy next up to try to make it easier to find out what's there to do and how to help.
Okay, thank you, Julian. It's really time to wrap up now. So I would like to take the chance to thank Lorenz, Jonas, and Julian for today's presentation. And of course, all of you for joining us today. We hope you learned a lot and you enjoyed the presentation. And please keep in mind that we will send you the recording of today's presentation by email, and make sure you stay tuned for future webinars. We wish you a wonderful day.